For our project, we decided to investigate how multiple factors involved in baking a mug cake would affect the total height after cooking in order to demonstrate the Calculus 3 concepts of traces and linearization. In setting up our experiment, we established that the two ingredients that we would use as variables would be both the amount of baking soda and the amount of milk. After cooking each mug cake for a minute 30 and then allowing it to rest for a minute, a resulting height was then measured and recorded for our data table. Through this process, we tested 25 different milk and baking soda combinations and then used this data to form a multivariable equation to fit the trends as seen in our data.
After we had finished collecting the data, our next plan of action was trying to find an equation that would approximate the shape created by our set of values. We first entered our data points into a 3D graphing application, setting number of teaspoons of baking soda as the x-axis, the number of tablespoons of milk as the y-axis, and the height of the mug cakes in centimeters as the z-axis. We then connected all of our data points with linear segments to help get a better visual understanding of the shape. The result was this: a 3D shape that looked like if you pulled up a single corner of a sheet of paper off a table. In order to find an equation to model the shape, we had to first analyze the graph's traces, namely the trace parallel to the xz plane and the trace parallel to the yz plane. In other words, we looked at the 2D cross-sections of the surface as they moved along a fixed axis where you treat one variable as a constant, and look at the 2D graph of the other two variables. In Excel, we made 10 different graphs. For example, this graph plots a cross-section parallel to the YZ axis when x equals 1/2. Basically, it plots the changes in height for every measurement of milk when we were using 1/2 teaspoons of baking soda. Likewise, this graph plots milk against height when we were using 1 teaspoon of baking soda. We graphed milk versus height graphs for every measurement of baking soda, and we made baking soda versus height graphs for every measurement of milk. The results were interesting. For the graphs on the YZ plane, milk versus height, the data seemed to be parabolic, and the steepness of the parabolas were increasing for each graph as x, the amount of milk, increased. Therefore, the trace in the x direction was also parabolic, so when x equals k, roughly we could estimate that the equation of the trace resembled z equals ay squared plus bk plus c, because for all values of k, the trace would be a parabola, and as k increases, so does the steepness of the graph. The graphs on the xz plane, baking soda versus height, showed a similar parabolic trend. They formed parabolas that steadily increased in steepness as y amount of milk increased for each graph. However, when y equals 0, the graph became a horizontal line with 0 slope. Therefore, the trace in the y direction was also parabolic, but y and x squared must be directly proportional to one another. So when y equals k, we could estimate that the equation of the trace roughly resembled z equals akx squared plus bk plus c, because when k equals 0, the graph will be a horizontal line, but as k increases, so does its steepness. We then combined the two traces into a single function that satisfied all the conditions. Z equals ax squared y plus by squared plus c, with a, b, and c being various constants. As you can see, both traces in the x and y direction are parabolic, but when y equals 0, z equals c, a horizontal line. But when x equals 0, the graph is still a parabola. Our next order of business was determining the values of a, b, and c. C was easy to find because when y equals 0, z equals c. So we found c by finding the average of heights when y equals 0, coming out with 3.84. We then found a and b by plugging in points and using systems. At 148.3, we got the equation 4.46 equals 48 plus 16b. At 3/4 for 6.79, we got the equation 2.31 equals 9/4 a plus 16b. We then solved the systems by subtracting the second equation from the first, coming out with 1.15 equals 1.75a, a equaling 0.65. We then plugged a back into the first equation and got b equals 0.11. So this is our final equation, z equals 0.65 x squared y plus 0.11 y squared plus 3.84. Plotting the equation on our 3D graphing application, we can see that the function fits our data points very well. Its shape closely matches our data points. Here is a more zoomed out version of its interesting shape.
As you may remember, linearization allows us to use a point on a given function and the partial derivatives of that function evaluated at the point to create an equation which allows us to approximate values. We are going to find the linearization of the following function, which models the height of the mud cakes, at the point 1/2, 4, 6. And then we're going to use that to approximate the height of the mug cake when we use 0.6 teaspoons of baking soda and 4.1 tablespoons of milk. As you may recall, the equation for linearization is as given. And in this case, the values a, b, and f of ab correspond to 1/2, 4, and 6 respectively. Given by the equation for linearization, we need to find first the partial derivatives. So first we find the partial with respect to x, which gives us 1.3xy, and then we substitute in the corresponding values. In this case, x is 0.5 and y is 4, and then we get that the partial with respect to x at 1/2, 4 is 2.6. Similarly, we're going to find a partial with respect to y, which gives us 0.65 x squared plus 0.22 y, and then we plug in the corresponding values, and we get that the partial with respect to y at 1/2, 4 is 1.0425. So now we plug these values back into the equation along with the values of a and b, and we get our linearization at the point 1/2, 4, 6. Now we have to evaluate this at 0.6, 4.1. So we just plug in and we get that at 0.6, 4.1, the cake is approximately 6.36 centimeters tall.